Good day, grade 11s, and welcome to Maths at Teneo. This is our grade 11 Maths homepage for term 3. And as you can see, there are a lot of topics that we are doing. We are focusing at the moment on trigonometric functions, and that's what we'll look at today. But I just want to show you all the other things that we have available to us as well. So we have a whole lot of extra resources with summaries and notes and extra exam papers, past questions, things like that. All things to practice our maths as much as possible. We have information on all of our SVAs, and those are our assessments, our tests and exams. So all the information is available to us here. We have memo discussions, that's from past tests and past exams, where the memo is given to us and there's a little video discussing exactly what should be answered in a test or an exam. And we have our submit independent study button. So that is in a brick and mortar school, we would call that homework. We call it independent study because all of our work is at home. So if we have a look at one of our topics, let's go into trigonometric functions and have a look there. So for every topic that we do, we have a homepage for that topic. And you will see for every single lesson that is taught, we then have theory behind the lesson. We have examples that we will cover in class, and we have the examples with the answers. So if we missed something in class, we didn't quite catch it, we can come and find that information. And then we have certain exercises that we are required to do as independent study to practice our work. And of course, we need the solutions to the independent study so that we know that we are doing the work correctly. So that is available there to us as well. So let's have a look. Today we're going to focus on lesson 3 of trigonometric functions, which is to do with period changes. So let's have a quick look. Just going to zoom in here. Right. So the period changes is shown or displayed on our graph by the influence of K. So in our normal sine and cos graphs, we have normally a period, which is the time or distance that it takes to finish one whole wave, one whole cycle, and it is normally 360 degrees. But if we now have something multiplying by x, a coefficient of x, so say if you look at the bottom here, we have a times sine k of x. So that kx, that is the coefficient of x, that is what changes our period. So we take 360 degrees, the original period, and we divide it by whatever that k value is. We all know that the tan graph is a little bit different. So if we are looking for the period of the tan graph, we take 180 degrees and we divide it by k. And in any graph, right, depending on the value of k, we will now have k number of cycles within the original period. So originally, our cos graph has a period of, or our sine graph as well, has a period of 360 degrees. So if we have a new graph, which is now y equals sine 3x, then we are looking at 3 waves or 3 cycles, so 3 repetitions within 360 degrees. If we look at y equals y equals cos half x, then we only have half a cycle within 360 degrees. And now the period is going to be 360 divided by a half, which is the same as saying 360 times 2, which gives us 720. So our graph is being stretched. And that is the influence of K. So we have this horizontal compression if we are multiplying it by a large number greater than 1. And we have this stretch if we are multiplying by something that is a fraction less than 1. Okay, and we can see here if we have y equals tan 2x, then we'll have 2 cycles within 180 degrees because our original period of tan is 180 degrees. So as you sketch these graphs, it's really important to divide all your x values on a standard graph by the k value, and also to take into consideration that you might have more waves within the original period. I want to take us now to our whiteboard where we can quickly look at exactly how our k value influences the graph. So if we have the function y equals sine 2x and we wish to plot this graph using a table, right, we can use our calculator and we're just going to substitute the values of x into this equation. So if we have y equals sine and we now have 2 times 0, that is still sine of 0, which is equal to 0. So we'll pop that into our table. If we then have y equals sine 2 times 45, we will have sine of 90, and sine of 90 is equal to 1. And we can continue this process. So let's pop that in there. Sine of 2 times 90, that gives us sine of 180. That is equal to 0. Y equals sine 2 times 135 degrees. That gives us sine of 270, which is equal to -1. Then we can have y equals sine 2 times 180. So notice each time we're taking our x value, we are substituting it because we are looking at the equation y equals sine 2x. So we're replacing that x with whichever x value we are working with in the table. 2 times 180 is sine of 360, and that is equal to 0. And by now, I'm sure you can see a pattern here. We have 0, 1, 0, -1, 0, 1, 0, -1, 0. And if you are concerned, you can check it on your calculator. But now what we can do is we can take these points as ordered pairs, so 0 and 0, 45 and 1, 90 and 0, and we substitute them, or we plot them on our graph here below. So if I draw a smooth curve to join all of these plots of these points that I have plotted, right? Ooh. There's our smooth curve. This is the graph of y equals sine 2x. And we can see here from 0 to 180, that is one wave or one cycle. And then from 180 to 360, we have another wave. And we can see this because it goes up and then down and it's ready to go up again. That's our first wave. And our second wave is then the same pattern, and it will repeat itself over and over again. So now the period of the graph has been compressed. We would say the period of this graph, the original period of the sine graph is 360. Now we are dividing because we have sine of 2x. We divide by 2. So now the period is 180 degrees, and you can see that from 0 to 180, that finishes one wave. So that influences the period of the graph. You can also compare it to the original graph. I'll quickly sketch it for you. If we have our normal graph of y equals sine x, right, it would look something like this. That is our normal y equals sine x graph, but now our graph has been compressed to fit two waves where we originally only had one wave. Hope you enjoyed the lesson. Have a wonderful day further.